spelling for your Dungeons & Dragons character's pee-pee size wrong.
Hey there, man. So what you got there is actually a triangle distribution curve, which is all fine and dandy, but if we want a statistically accurate way to roll for fantasy schmeat, then we're going to need a little bit of stats work, which, lucky for you guys, I just got a master's in econometrics, and I cannot think of a better way to pop its cherry than on some fantasy schmeat. Wait a minute. So you're totally right. This is called a bell curve, also known as a normal distribution curve. And the idea behind it is that the more observations you have, aka the more dice you roll, the more your possibilities are going to start looking like this. It's because of something called the law of big numbers. Technically, it's called the central limit theorem, but I'm not fucking calling it that. What am I, a cop? It's the law of big numbers. It's big numbers. It's exactly why your 2d6 distribution looks a lot closer to this than 1d20. Basically, as the number of dice that you roll increases, that distribution is going to look more and more normally distributed. That's the way it works, baby. Here's the distribution for 2d6, and here's the distribution for 4d20. As you can see, 4d20 looks a lot more bell curve, but the issue is, unless you're going to carry around a 200-inch long meat lasso everywhere you go for the rest of the campaign, all stealth checks at disadvantage, by the way, then you kind of need to put this into a workable unit. Easiest way to do this is to just divide it by the number of observations, aka the number of dice rolled. So 4d20 divided by 4 gets you a bell curve looking like this, which is looking pretty good, but there is a problem here. As you use this method, the dividing by the number of dice you're using, the higher and higher you go, the tighter this distribution is going to become. So it turns from this to this, as all your observations are sort of pushed in. It's got a little thematic. Let me just... If you really want a statistically accurate way to calculate the dingling size of your charming, puckish rogue sorcerer, original idea by the way, then all you really need is a D100. And an understanding of standard deviations and z-scores. We'll get there. Don't panic, don't panic. Standard deviation is basically just a measure between the variance of your values in your data set and the average of that data set. It's not that important, don't worry about it. The important part is that since we have normally distributed data here, then we get to use the empirical rule, which states that 99.7% of all observations are within 3 standard deviations of the mean. And when that happens, we can also use z-scores. Don't worry, I'm not gonna, trick you into learning formulas. Oh, fucking got ya! The z-score is actually just a measurement of how many standard deviations your observation is away from the mean. Basically, it's just how many standard deviations is your PP away from the average size of PP. Can I just say cock and ball? This is how you calculate z-score, and then when you solve it and flip it around, this is how you would calculate PP size. This is going to be on the test, kids. So, X is our PP size. This is just the average PP size. That's our z-score, and then that's our standard deviation. According to the incognito tab on my phone, the average PP size is 5.16 inches, and the average standard deviation is 0.56 inches. That's what the study said. All bodies are beautiful. All we need to solve for our PP size is our z-score. But wait, I know what you're thinking. How do we calculate that z-score? Where's it coming from? Super easy. All you do, you take a D100 and you roll it. This is a percentile, alright? So I got 79%. Now, all you simply do is you locate 79% on your z-score table. You don't have a z-score table printout? Do you even like Dungeons & Dragons? Brennan Lee Mulligan is gonna hear about this. My 79 is somewhere around a 0.81 z-score. And now, you just plug and chug, baby. All you do is you take your average PP size, 5.16, and then you add your z-score multiplied by your standard deviation. So it's 0.81 multiplied by 0.56. Multiply those together, add them to your average, and you have a 5.61 inch PP. Congratulations. These would be the numbers you would use if you wanted your art to imitate life for whatever reason, and have the average PP size in your fantasy world be the same as it is in the real world. But the cool part is that we can edit these numbers dependent on race, lineage, whatever. So let's say in your world that halflings are packing the schmeat, okay, as God intended. So their average is going to be a lot higher than that 5.16. Let's say 12 inches, right? That's the average. And let's say in your world, people know that if they hook up with a halfling, they are consistent, man. So that would mean that the standard deviation is going to be a lot smaller because they know 12 inches is pretty much what you're going to be getting. The best way to do this is your standard deviation would just be lower. With that, you can roll your percentile dice again, look up your z-score, multiply the z-score by the standard deviation, add that to your average, and look at that. Your halfling now has a 12.081 inch PP. Let's go on to orcs. Maybe every orc is like a box of chocolates. You just don't know what you're gonna get. So your average is gonna be average. We can say 6 inches. Meanwhile, the standard deviation would be super high, super crazy. Let's say like 3. So you can either get like an orc that's absolutely packing it, or one, you know, good things come in small packages. So all we would do, we grab our percentile, we roll it. That is an 82, 0.92. Which is a final calculation of 8.76 inches. This is the statistically and mathematically most accurate way to calculate your skin flute size. So until you dweebs start bringing z-score tables to your session 0, you're doing it wrong, okay? What am I doing with my life?